Hello, in this video I'm going to solve question 6 from problem set 1. Let us read the question together first. Show that the function d defined on the Cartesian product of r by r to r defined by dx and y equals to absolute value of x minus y over 1 plus the absolute value of x minus y is a metric on D. Describe the circle COR centered at the origin with radius r. Consider all cases for different values of r. Okay, so to do this, we have to show that this function d defined in this way satisfies 4 properties that we expect for a metric. The first property is that the output of D should be a non-negative number for every choices of x and y from the set of real numbers. But this is automatically satisfied by this definition. Why? Because the output of the absolute value of x minus y for all choices of x and y in R is greater than or equal to 0. So the numerator is non-negative and the denominator is strictly positive. Yes? And then when I divide these two numbers, definitely the final number is greater than or equal to 0, regardless of the choices of x and y. So the first condition is satisfied. For the second condition, I need to prove this. I need to prove that for all x and y in R, dx and y equals to 0 if and only if x is equal to y. So that is what I want to prove. Okay, so let us say that let x and y be in R, dx and y is equal to 0 if and only if the absolute value of x minus y over 1 plus the absolute value of x minus y equals to 0. But this is a fraction. This fraction is equal to 0 if and only if its numerator is equal to 0 and its denominator is not equal to 0. But it is guaranteed that the denominator is not equal to 0 because this is a non-negative value, and when I add 1 to it, it becomes a strictly positive. So this means that this is if and only if the numerator is equal to 0, but absolute value of a number is 0 if and only if the number itself is equal to 0, and this happens if and only if x is equal to y. So we are done. The third property is this. I need to show that for all choices of x and y in R, it doesn't matter if I calculate dyx or if I calculate dxy. In other words, I need to show that D is symmetric. But that's also clear. For example, let us say that x and y are arbitrary real numbers. Then I ask you to calculate d, y, and x. So you need to interpret it in this way. So x is the first component, it appears here and here, and y is the second component, it appears here and here. Of course, here my first component is y, and my second component is x. So if I want to write it according to what is given in the problem, I have the absolute value. I write my first component, which is y, minus the second component, which is x, and for the same thing, and the same thing for the denominator. But from your elementary studies, you know that there is no difference between absolute value of x minus y and the absolute value of y minus x. So in that case, I can just replace it and write it as absolute value of absolute value of x minus y over 1 plus absolute value of x minus y again, but this is exactly dx and y. So we showed that regardless of my choices of x and y, this is equal to that one. Okay, so the last thing that I need to prove is the triangle inequality. So what I do, I would say that let we need to show that for all choices of x, y, and z in R, I need to convince myself that dx and z is less than or equal to dx and y plus dy and z. Okay, in other words, if I want to translate this into the language in this problem, the left hand side becomes absolute value of x minus z over 1 plus absolute value of x minus z. I should show that this is less than or equal to d of x and y is the absolute value of x minus y over 1 plus the absolute value of x minus y plus the absolute value of y minus z divided by the 1 plus the absolute value of y minus z. Okay, so sorry, the last one is also absolute value. Okay, I need to convince myself about this question mark. So x, y, and z are arbitrary real numbers. I want to convince myself that this is indeed the case. Okay, I will solve this. I want to prove this inequality in two different ways, but let me just do the more elegant one here. So to do that, let me take this inequality with me to the next page. Okay, so this is the inequality I want to show. Okay, first I introduce two new variables. I would say that let u be equal to absolute value of x minus z and v be equal to the absolute value of x minus y plus the absolute value of y minus z. Okay, if you have followed my lectures in the second lecture of the transition to advanced mathematics, we showed that this number is less than this number. So we know that u is less than or equal to v. On the other hand, of course, we know that u is also non-negative because it is the output of an absolute value. Okay, what I do, I add uv to both sides. So you need to be patient a little bit to see why it works. So this is one of those problems that you have to be patient to see why this method is working, and it reveals itself to you at the very end. But you need to follow me that every step that I am taking is actually mathematically valid. So we know that u is less than or equal to v. We had the proof of this in the lecture. Now I use this fact, I add uv to both sides. On the left hand side, you see that I can factor a u out, and on the right hand side I can factor a v out. Okay, and then what I do, I divide this side and both sides actually by this combination. Yes, I want to do that, and this is possible because u and v are non-negative, so when I add 1 to them, so this product is positive, so it doesn't matter. So I'm not worried about dividing by a negative number or something like that. Okay, so what I do when I divide that, and this one and that one are gone. When I do the division on the right hand side, this one and that one are gone. So u over 1 plus u is left on the left, and v over 1 plus v is left on the right. So if I do that, I will get this. U over 1 plus u is less than or equal to v over 1 plus v. Okay, and now I replace these absolute values instead of u and v. So what does it mean? It means that instead of this u and this u, I plug absolute value of x minus z. Is less than or equal, and instead of this v and that v, I plug this in. So this becomes absolute value of x minus y plus the absolute value of y minus z. over 1 plus absolute value of x minus y plus the absolute value of y minus z. Okay, so you see that this is the inequality that I want to prove. At least the left-hand side of this inequality that I have proven so far is exactly the left-hand side of this inequality. Of course, I have to manipulate the right-hand side a little bit. But what I can do, I can take this one and then divide it by a denominator. Means that I want to decompose my fraction into this piece that you see now plus this piece, yes? So you will see what is the benefit. So I would write this is equal to the absolute value of x minus y over 1 plus the absolute value of x minus y plus the absolute value of y minus z plus my second fraction will be the absolute value of y minus z over 1 plus the absolute value of x minus y plus the absolute value of y minus z. And now this is less than or equal to the absolute value of x minus y over 1 plus the absolute value of x minus y plus the absolute value of y minus z over 1 plus the absolute value of y minus z. Let me explain why. So, to understand this, compare this fraction only with this fraction. You see that the numerators are exactly the same, but the denominator here is greater than or equal to the denominator here. Why is that? Because 1 here is 1, absolute value of x minus y is absolute value of x minus y. I have an extra non-negative term in the denominator of this fraction. So in total, the denominator that you see here is greater than or equal to the denominator that you see here. The numerators are identical. So that is clear that this fraction as a whole is less than or equal to this fraction. Exactly with a similar argument, you will see that this fraction is also less than or equal to this fraction. Why? Because again, the numerators are identical, and the denominator here has this term has this extra term in its denominator. So the denominator here is greater than or equal to the denominator here. And now look, what you have here, which is the left-hand side of this inequality that you want to show, is less than or equal to this expression. This expression is equal to the sum of these two expressions, but the sum of these two expressions is less than or equal to this sum. So this means that this expression is really less than or equal to this expression, and that is exactly the proof to this question mark. So I am done. So this means that this is really a metric. Okay. But the second part of the problem is that O is the center, is the origin of the real numbers, and R is actually the radius. We want to describe the circle centered at the origin with radius R for all different possible values of R. Okay, so the first thing that I want to do is to write the definition of my circle. So circle centered at O with some radius R is the set consisting of all real numbers x according to the definition of a circle we had in the lectures. The distance from x to the 0, yes, because the point corresponding to the origin is 0, is equal to R. But then, so if I compare this one with that one, here 0 is y. So instead of y I put 0, then I will get this expression. So the set x in R, the set consisting of all real numbers such that the absolute value of x over 1 plus the absolute value of x is equal to R. Okay, so for different values of R, we want to discuss about these circles. The fun thing I want you to know is that the absolute value of x is definitely strictly smaller than 1 plus the absolute value of x. And on the other hand, it is non-negative. So if I divide both sides by this expression is strictly positive. So I divide that, then I will get the absolute value of x over 1 plus the absolute value of x is less than 1. So this means that the output of this expression is a number which is greater than or equal to 0 and is strictly less than 1. Okay? So this means that if R is a number equal to 1 or greater than 1, this set is empty, because this is not possible for this expression to reach to 1 or a number larger than 1. So we can say that, okay, if R is greater than or equal to 1, then COR is actually the empty set. Okay, so then what happens if R is equal to 0 or greater than 0? So we can consider both in one case, yes? So what happens if R is greater than or equal to 0 and less than 1? Then in that case, absolute value of x over 1 plus, okay, so let me take this off and put semicolon here. Then absolute value of x is equal to R. Let me look for possible values for x. This becomes absolute value of x is equal to 1, R plus 1 absolute value of x. Then absolute value of x is equal to R plus R times absolute value of x. I move the second term to the left. It becomes absolute value of x minus R absolute value of x is equal to R. I factor absolute value of x out is equal to R. So what happens is that the absolute value of x becomes R over 1 minus R, and I am on the safe side to divide by 1 minus R, because R is strictly less than 1, so I am on the safe side. 1 minus R is not 0. Okay, and then if I am looking for x, so x becomes plus or minus R over 1 minus R. By the way, this expression is non-negative. Why? Because R is non-negative, 1 minus R is positive, so this is non-negative. Okay. Of course, in the extreme case that R is equal to 0, both signs plus or minus gives rise to the 0 value. So we can say that, okay, C, O, and R is equal to the set consisting of these two elements, minus R, 1 minus R, and R, 1 minus R, if R is strictly between 0 and 1, and it is just 0 if R is indeed equal to 0. So we actually answered the problem in all cases. If R is greater than or equal to 1, this is the empty set. If R is equal to 0, COR only contains the 0 number, okay? Because this is the set of real numbers, so this is not O, this is 0. And then if R is between 0 and 1 strictly, then my circle consists of exactly two real numbers. One of them is R over 1 minus R, the other one is negative of that number. So here the problem is solved. But now you see that when I wanted to prove the triangle inequality, I did it not in a standard way. I want to show you now that if you follow the standard strategies to prove inequalities, in this case you can do that. So what is the general strategy to prove inequalities? Okay, so let me go to the next page and paste this inequality once more here. So this is the proof, this is the inequality that I want to prove. Usually the general strategy is to start simplifying the given inequality in a reversible way. So you take some steps to simplify your inequality, but in each step you have to make sure that this step is reversible. And then you continue this so that you reach to an inequality which is guaranteed to be true. And now, because all these steps that you have taken to reach to the simpler inequality is reversible, it means that the original inequality that you are supposed to prove is equivalent to the simpler inequality that it is somehow guaranteed for you to be true. And because that simpler inequality is true, the original inequality is also true. This is the logic behind that. I'm not saying that this method always works to prove inequalities. No, there are very hard inequalities that you cannot prove it like this. But this is the main and general technique to start proving inequalities. But of course here, if I want to simplify this expression in its form, I have to copy and paste these symbols a lot of times. For simplicity of writing, it's better to introduce some abbreviations, some shorthands. So I would say that let me, instead of saying absolute value of x minus z, let me introduce alpha to be the absolute value of x minus z, beta to be absolute value of x minus y, and gamma to be the absolute value of y minus z. And now the question mark reads like this. So my goal is to prove that alpha divided by 1 plus alpha is less than or equal to beta divided by 1 plus beta plus gamma divided by 1 plus gamma. Okay, so this is my question mark. Now I start simplifying this inequality. I just want you to know this inequality is nothing except the original inequality. I have introduced these symbols to write it simpler. Okay, so what I do, I multiply. I want to try to simplify this inequality. One way is to get rid of the fractions. So what I do, I multiply both sides. Let me write it here. So I multiply both sides of this inequality by 1 plus alpha, 1 plus beta, and 1 plus gamma. By the way, these numbers are positive because alpha, beta, and gamma are non-negative. They are outputs of absolute values. So I don't need to be worried about the direction of this inequality. I have to keep it the same. But when I multiply this on the left-hand side, this one and that one are simplified, and then this expression is multiplied here in the numerator. When I multiply this here, this one and that one are cancelled. These two terms are left, which are supposed to be multiplied here. And similarly, when I multiply this here, this one and that one are gone. These two are left, which is multiplied here. Okay, so what I do. So it means that I multiply that. It becomes alpha, 1 plus beta, 1 plus gamma is less than or equal to beta, 1 plus alpha, 1 plus gamma, 1 plus alpha, 1 plus beta. But the important thing that you have to pay attention is that this is reversible. How? From here, I can divide the left-hand side and the right-hand side by this expression. It is clear that I will go backward and get this back. Okay, so this is reversible. This is important. Now, I expand these expressions. So alpha, I multiply them. 1 plus beta plus gamma plus beta gamma is less than or equal to beta. 1 plus alpha plus gamma plus alpha gamma, and then plus gamma, 1 plus alpha plus beta plus alpha beta. It's also reversible, yes, because I can just simply factorize these terms. And then I multiply alpha in, so alpha plus alpha beta plus alpha gamma plus alpha beta gamma is less than or equal to beta alpha beta beta gamma and alpha beta gamma plus gamma plus alpha gamma plus beta gamma plus alpha beta gamma. And now what happens? This alpha beta gamma and this alpha beta gamma are cancelled. This alpha beta and this alpha beta are cancelled. This alpha gamma and this alpha gamma is cancelled. And the important thing is that this is also reversible. Sorry, let me change my color. Okay, then what I'm going to do, there is one single alpha left here. I move it to the other side. Okay, what is left on the left hand side is just simply 0. And on the right hand side, as you see here, I have here beta, I have here gamma. I move alpha to the other side, it becomes minus alpha. So I combine them into one pair of brackets, so it is beta plus gamma minus alpha, and then plus. But of course there are more terms left. So a beta gamma is left here, a beta gamma is left here, so it means I have 2 beta gamma, and I also have 1 alpha beta gamma left. Okay, but and then again, this is also reversible. So you see that this inequality has been simplified to this inequality in reversible ways. All the way down here, they are reversible. Okay. But it seems that I cannot simplify this anymore, but to be honest, I really don't need to do that. Why? Because this is true. Why this is true? First of all, alpha, beta, and gamma are the outputs of absolute values. So alpha, beta, and gamma are non-negative. If they are non-negative, what does it mean? It means that this expression, so let me change my color. So this expression is non-negative. This expression is also non-negative. But this part is not that trivial as the other two cases, but still that is true. Why? Because again, in the lectures we showed that this number is less than the sum of these two numbers or equal to it. So we know from the lecture that alpha is less than or equal to beta plus gamma. So this means that 0 is less than or equal to beta plus gamma minus alpha. So yes, this expression is also non-negative. And now the right hand side is the sum of 3 non-negative values. Definitely the sum is a non-negative value. So what I can conclude is that this inequality is indeed true. And this inequality indeed true means that this original inequality is also true because of all the operations are reversible. So the reason that I brought this up is I just want to show you that even if you cannot find that a little bit creative way to prove the triangle inequality, but still you have a very good chance to be able to prove it using the general strategy to tackle inequalities. What is that general strategy? Is to simplify the given inequality in a reversible way until you reach to a simplified version of that inequality which you can guarantee to be true. Okay. I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.